This video will conclude with a proof of Euler's formula. Along the way, we will need to prove two key derivatives. We'll begin with the derivative of an exponential function. An exponential function consists of some constant base raised to a variable power. The variable exponent is the input of our system. So, recalling the definition of differentiation, let's plug in the exponential a to the x. We can simplify this by recalling a couple rules of exponentials, then taking our exponential a to the x out of the limit, since it contains no h. Let's ask, does there exist some constant a such that the derivative of a to the x is equal to a to the x? For that to be true, we would need the limit as h goes to 0 of a to the h minus 1 over h to be equal to 1. Instead of solving for a directly, we're going to manipulate the form of the equation into something familiar. Let 1 over n equal h, so that we have the limit of 1 over n going to 0 of a to the 1 over n minus 1 over 1 over n equal to 1. Note that the statement 1 over n going to 0 is the same as n going to infinity, and multiply both sides of the equality by 1 over n. Add 1 to both sides of the equality, then raise both sides to the power of n. A is equal to the limit as n approaches infinity of 1 plus 1 over n raised to the nth power, which is our definition of Euler's number. We have shown that if we want an exponential function to be equal to its own derivative, then Euler's number must be the base of that function. Similarly, we could show that the derivative of e to the nx with respect to x is n times e to the nx, and the antiderivative of e to the nx times dx is equal to 1 over n times e to the nx plus c. Our next important derivative is the derivative of a sinusoid, which follows naturally from the derivative of exponential functions. Recall that cosine of x is equal to 1/2 times e to the jx plus e to the negative jx, where j is the imaginary number. By the linear combination rule of derivatives, we can then say that the derivative of cosine of x with respect to x is equal to 1/2 times the derivative of e to the jx with respect to x plus 1/2 times the derivative of e to the negative jx with respect to x. We just proved that the derivative of e to the jx with respect to x is equal to j times e to the jx, and that the derivative of e to the negative jx with respect to x is equal to negative j times e to the negative jx. Next, let's pull the j over 2 term out. Recall that 1 over j is equal to negative j, so that we can substitute negative 1 over j for j in the equation. The term in the brackets is our definition of sine of x, so we have shown that the derivative of cosine of x with respect to x is equal to negative sine of x. I'll leave it to you to prove that the derivative of sine of x with respect to x is equal to cosine of x. It follows that the antiderivative of sine of x is equal to negative cosine of x plus c, and that the antiderivative of cosine of x is equal to positive sine of x plus c. If these results surprise you, go ahead and plot the functions. Remember that the derivative can be thought of as the instantaneous rate of change of a function. Observe, for instance, that when x equals pi, cosine of x is going from a decreasing function to an increasing function, meaning that its instantaneous rate of change is 0. Negative sine of pi is equal to 0. Observe that cosine of pi over 2 is the largest rate of negative change, and that is the lowest point of negative sine of x. I'll leave further observations up to you. We now have the tools to prove Euler's formula. This proof, as the culmination of all the steps that preceded it, represents the final necessary background to signal processing, and concludes this series on necessary background to the study of signal processing. Euler's formula states that e to the I theta is equal to cosine of theta plus I times sine of theta. Instead of deriving the statement itself, we're going to prove it to ourselves by testing to make sure it's valid, given our definitions. First, we multiply both sides of the equation by e to the negative I theta. Next, we take the derivative of both sides of the equation. We know that the derivative of a constant is 0, so the right hand is 0. For the left hand, we recall the product rule for derivatives, and we are left with negative I e to the negative I theta times cosine of theta plus I sine of theta, plus e to the negative I theta times negative sine of theta plus I cosine of theta. We then multiply in the negative I, then pull out I times e to the negative I theta so we can combine terms. What's inside the bracket is 0, and 0 times anything is 0. So, we've shown that our original equality, Euler's formula, holds after we have just made a bunch of manipulations based on definitions. To summarize, the derivative of e to the nx with respect to x is n times e to the nx. The antiderivative of e to the nx with respect to x is 1 over n times e to the nx plus c, where e is Euler's number. The derivative of cosine of x with respect to x is negative sine of x. The antiderivative of cosine of x with respect to x is sine of x plus c. The derivative of sine of x with respect to x is cosine of x. The antiderivative of sine of x with respect to x is negative cosine of x plus c. Euler's formula states that Euler's number raised to the power of an imaginary number, I, times theta is equal to cosine of theta plus I times sine of theta.